Let's consider this next homogeneous or non-homogeneous equation where our g of x is already identified to be exponential. As you can see here, we have the notation for exponentiation. And for this, we can solve this using this general solution, y equal to y sub c plus y sub p. Now, y sub c is the complementary solution of this equation if the g of x, or the equation or the function that can be found on the right hand side, is expressed equal to 0. Of course, if it's equal to 0, then our equation would be homogeneous, and we're just simply going to use the same processes involved in solving homogeneous equations. But this time, since it's not equal to 0, that's just part of the solution. Y sub p, the second part of the solution, is expressed in this table here. Now, this table have specific forms of y sub p, and since our g of x is exponential in notation, let's look at the 7th row, and then our y sub p is a e to the power of the same exponent that can be found on our g of x. We have 4x. In this time, we are just going to solve for a later to come up with the correct y sub p to be combined with y sub c. So let's start with y sub c here. As mentioned, we could have the same process of solving homogeneous equation because we will have here this equation with differential operator d expressed in this manner, d squared minus 3d plus 4 of y is equal to 0. Okay? And with that, our auxiliary equation is m squared minus 3m plus 4 equal to 0. The next thing here is to solve for the roots of this auxiliary equation. And let's find out the correct general solution because we have 4 different situations. Number 1, if the roots of the auxiliary equation are all real, but they are distinct, meaning they are different from one another. We also have another form if the roots are real and there are multiplicity or repeated roots. We also have other rule for when our roots are imaginary, and if the roots are imaginary and there are repetitions. Let's check here. There are a lot of ways to solve for the roots of this. Of course, we could have a factoring, you could have completing the square, but since I believe if you're going to have completing the square, this will take a lot of time. Let's use, of course, the commonly known as our, they call this one, quadratic formula. Okay, our a here is 1, b is minus 3, and c is 4. This can be factored because your ac is 4. Okay, factors of 4 that when added will result to negative 3. That's 4 times 1 plus, that's 5, right? Negative, negative, negative 5. 2 times 2 is also 4 and negative 4. So the factoring method cannot be used. So again, as mentioned, we'll be using here the quadratic formula. So instead of x, we'll have m is equal to negative b plus minus the square root of b squared minus 4ac all over 2a. Okay, let's see if what would be the roots here. So negative of negative 3 plus minus the square of negative 3 minus 4 times 1 times 4 all over 2 times 1. So you have here positive 3 plus minus, you will have here 9 minus, if I'm correct, yes, 16 over 2. Then you have here 3 plus minus square root of negative 7 over 2. And with this in mind, we can now identify that our roots are imaginary because we don't have a square root of a negative number. You can continue writing it here. M is equal to plus minus, let's have 3 plus minus, you will have square root of 7 times square root of negative 1 all over 2. That's actually 3 plus minus a square root of 7i over 2. Okay? Or if you would like to separate them, because our roots, if imaginary, can be expressed in this manner, to identify the correct a and b, we will have here 3 halves plus minus square root of 7 halves I, giving us the a, which is not the same a here. The a in the point of imaginary numbers is 3 halves, and your b is square root of 7 halves. We need this Because for imaginary roots, the general solution, y sub c, is equal to this manner. You have e to the power of ax times c sub 1 cosine of bx plus c sub 2 sine of bx. These are the a and b we're going to use, not this here because these were already used in the solution of our roots. So our y sub c, again, we are still on y sub c, e to the power of your a, which is a 3 halves x, if I'm correct. Okay, please take note of that. 3 halves x times c sub 1 cosine of your b, which is square root of 7 2x plus c sub 2 sine of square root of 7 all over 2x. This is just for your y sub c. Again, just for your y sub c. Now let's move to y sub p. Our y sub p is expressed in this form. Let me rewrite it here. A e to the power of 4x, because our original equation is minus 3 plus 4 is equal to, let me go back here, 3 e to the power of 4x. We need to come up with a process in solving the coefficient a by looking into this one here. Because instead of y double prime, y prime, and y, we'll be using y sub p. And of course, to substitute with these two, we need the first and second order derivatives of y sub p. So the first order derivative of y sub p, taking this as constant a, the derivative of e to the power of 4x is just e to the power of 4x, it's just the same. But what is added here is the derivative of your exponent according to the chain rule. So you have 4. In short, your first order derivative of y sub p is a 4, or let's say 4a e to the power of 4x. Now for our second order derivative of p, we will derive this as well. So you will have 4a, again, a derivative of e to the power of 4x is itself, but we need to add here or multiply the derivative of the exponent, which is still 4. So the second order derivative is equal to 16a e to the power of 4x. We need this one here and this original, because we will be substituting that on our original form. Instead of the y's, we will have the y sub p's, just to solve the value of the coefficient a. So let's start here. So we'll have 16, this one, a e to the power of 4x minus 3 times the first order derivative, 4 a e to the power of 4x plus 4. Sorry, let me move this here so that I have space here. 4 times this, so you have a e to the power of 4x. These are all equal to 3e to the power of 4x. So we have here 16a e to the power of 4x. This is minus 12a e to the power of 4x plus 4a e to the power of 4x equal to 3e to the power of 4x. Combining this, 16 minus 12 is 4 plus 4, 8. A e to the power of 4x is equal to 3e to the power of 4x. Solving for a, divide by 8 e to the power of 4x to cancel this and that. Doing the same thing on the other side. We'll remove this. So your a is a fraction 3/8. This is the value of your a. Therefore, your y sub p, which is expressed as a e to the power of 4x, will then be equal to 3/8 e to the power of 4x. This is your y sub p. With this and your y sub c earlier, as mentioned, the solution is the combination of both. So you will have, this is your y sub c. Let me copy this. Okay. Let me go back here. Y is equal to y sub c plus y sub p. So your y sub c is, we have 3 halves x, and your b is square root of 7 halves. So you have e to the power of 3 halves x times c sub 1 cosine of square root of 7 over 2x plus c sub 2 sine of square root of 7 over 2x. That's just your y sub c. Then plus your y sub p, which is 3/8 e to the power of 4x. This is your entire solution, combining the complementary and particular solution of the given equation. So we're able to solve this because we're able to remind ourselves with the quadratic formula in the situation of our general solution if our roots are imaginary, and then using the table earlier for y sub p together with the necessary processes. Thank you very much for watching.